Okay. In non-restoring division method, see, the procedure is same. In restoring division method, first we perform the subtraction. Divisor is subtracted from the dividend. Okay, if it is wrong subtraction, means if you will be getting a EBIT, if you are getting EBIT as 0, it means the subtraction should not be done. A minus B resulting negative result, right? As per the restoring division, we will be subtracting. If your EBIT is 0, it means the result is negative, A minus B. You should not perform the subtraction. So we are going to shift left side and then we follow the subtraction. Before doing that, because previously we have did the subtraction which should not be done, that we are doing back by restoring, by adding the divisor again to the A. Okay, this is what restoring division. In non-restoring, we won't add here, but we will shift and then we'll add. If your result is A less than B, rather than adding here itself, which restoring, we won't do this here, but after shift and we will add this. Okay, so that assuming the result is both the same. See, here we are doing A minus B. If A less than B, we are adding B, right? A minus B. If A less than B, we are restoring back by adding B. Okay. After this, what we are doing? We are shifting left side. This is nothing but a twice. Left shift is nothing but multiplying by 2. And then again we are subtracting. Okay. So that will result you to capital A minus 2 capital A
minus B.
Minus B, yes. Minus 2B to A minus B. In restoring method, rather than adding here, we'll be doing first shift, after that we will add. Okay, so A minus B we are doing, rather than adding here itself, we will shift this left side. So shifting left side is nothing but multiplying by 2 and then we will add B. So this results again the same result, 2A minus B. Okay, so in both the cases the result is same. Okay, if only this condition you have to add B if it is the wrong subtraction previously. How would we know that the subtraction is wrong? Based on the EBIT here, if E is 0, it means A less than B. Okay, so if A less than B, then only you have to add. If A greater than B, there is no case of restoring the division. The normal as usual process will go on. Okay, so if A less than B, then you have to shift and then add B. If A greater than B, then the previous subtraction is correct. There is no point of restoring or non-restoring division. Okay, so if A greater than B, we continue as usual subtraction. If A less than B, we have to restore and then do. So that we are doing here. After shifting, we will add b. Okay. So if a less than b, we will add b. If a greater than b, we will subtract b. That is in the next cycle. Okay. Right. This is one thing. And second thing, restoring method is suitable for sign magnitude numbers, but non-restoring method is for two's complement numbers, representing two's complement form. Okay, only two's complement numbers it is suitable. Okay, so this point I forgot. So hence our representation of the numbers is different. Accordingly, the flow chart will vary. So let us come to the flow chart. In non-restoring method, A holds, see, if both the divisor and dividend are same size, then M will be the divisor, or here we used to take earlier B. Here B is similar to M, and Q is the dividend. Actually, A and Q forms the dividend, total dividend, right? If it is double the size, A and Q holds the total dividend. Count is equal to number of bits in your divisor. Okay, number of bits in your qubit. Of course, as per computer point of view, all the registers are of same size. I can say number of bits in a dividend Q, which is equal to the number of bits in divisor as well as A, which we can take it as N. But the difference here is all these numbers will include the sign component. Next, A less than B, A less than 0. It means the most significant bit of A we are checking, right? Initially we assume we will start proceeding by subtraction, right? So initially there won't be any previous values of your Qn values or E values. So we start with subtraction. We start with shifting AQ and then we proceed for subtraction. So after subtraction, because we are doing it 2's complement way, right? The numbers are of 2's complement. So after subtraction, subtraction here is implemented by taking 2's complement of divisor and adding it to A. Okay. So if you get A less than your divisor, it means the result is negative. So negative result means your most significant bit of A is 1. Okay, so that says the result is negative. So A less than 0 indirectly. So you can check MSB of A, or else it indirectly shows that A less than 0, right? If your result is less than negative, if your result is negative, it means the subtraction should not happen. Okay, so present Qn bit. The divisor can divisible by 0 times. So present Qn bit, we will make it 0, and then we decrease the count and proceed by addition. Okay, so if the previous value of Qn is 0, when it is 0, if your result is negative, when the result is negative, if A less than the divisor. Okay, so if A less than 0, the previous value of Q is 0. Okay, so 0 times the divisor is gone into the dividend, because the dividend is lesser than divisor. 0 times only it can go. Okay, after shift you can perform the division, right? So if A is equal to, most significant bit of A is 1, it means A less than 0. If most significant bit of A is 1, then Qn is 0. Okay, so if Q is 0, it means most significant bit of A is 0. Then you have to go by shift left and then add. Okay, because previous subtraction you should not happen, so you have to shift left and then add. Okay, so if A greater than 0 here, the subtraction is correct, I can make the present quotient bit as 1, and then I can proceed by shifting it left in the next cycle, shift left and then subtract the divisor. Okay, This is a simple algorithm. You have to follow the same steps. So let us see the example that we made a mistake in the earlier class. So restoring division algorithm. This we have seen in restoring method, same 213, we got the correct result. So quotient is 15, remainder is 5. Similarly, non-restoring method, this is what 200, right? So this 200, 2's complement data you have to convert. So this is your 200 is nothing but this value. Okay, so you have to add a 0 extra to this, saying it is a plus 200. Similarly, 13 plus 13. Okay, see, this is one way. This is your total dividend. Okay, and this is your divisor, right? Okay, so load your dividend in the registers A and Q. Okay,
Ma'am,
yes,
ma'am, we are saying PowerPoint, ma'am.
it is in PowerPoint.
Yes, ma'am.
Now,
Yes, ma'am. Now we can see word.
okay. So non-restoring method. See, your dividend is plus 200. 200 is this value, right? 1100, 100 is 200. Since it is plus, so I have added most significant bit as a 0, indicating that it is a plus result. Similarly, divisor 13 plus 13 as 0, 1, 1, 0, 1. I want minus 13 because the divisor has to be subtracted sometimes, added sometimes. So I want minus 13. So that I have calculated, but this is nothing but your minus 13 in 2's complement. So non-restoring division method suitable for 2's complement data only. Okay, not sign magnitude form. This need to be remembered. So your dividend is loaded in A and Q registers. Like this I have loaded, so that number of bits in Q are 4. So my sequence counter is 4. This is one way. If you have ambiguity, making all the sizes of the registers as same, I can do like this, because the divisor is 5 bits, right? Your dividend registers A and Q should also be 5 bits. So if I make it like that, I can make 2 zeros. I have to add. This is first A and then second Q. Okay, so you can work with this data also. That also gives the same result. It should give the same result, and it is giving. I have checked also. So now your A will be this value 00110, and Q will be 01000. Then the sequence counter becomes 5. Okay, either ways the result is same. Am I clear?
Yes, ma'am.
Okay, so we start with the operation. A is loaded here. This data I have taken. Okay, so this data I have taken. If you want me to do, we will do this also. Both are same. I'm getting the result. I have checked it. This is your A, and the Q is loaded with this. So 1000. So sequence counter is 4, because the number of bits in Q, because these 4 bits we need to check. Finally, Q holds the dividend, A holds the divisor. Remainder. Q holds the quotient, A holds the remainder. Okay. So this is your sequence counter 4. Initially, assuming the previous value of Qn as 1, initially you have to go by the path subtraction. So before going the subtraction, I have to shift the register SHL AQ. Okay, I have to shift A and Q left side by 1 bit. So after shifting, these are the values, and this is the new Qn value that is unknown right now. Okay, I don't know the value of this. That has to be fixed after subtraction. Okay, if the subtraction is true, then Qn will be 1. If the subtraction is false, then Qn will be 0. Okay, So I'm doing the subtraction, nothing but minus b I have added, which is 10011. After adding, this is what the result. Here the most significant bit of a after subtraction is 0. It means a greater than 0. It means the result is positive. So subtraction, we can do the subtraction, so that itself says that the quotient term is, that particular bit is 1. Okay. So I am making Qn as 1. I have to set Qn 1 at this stage if the result is positive. Okay. So with this, first cycle is finished. So my sequence counter is reduced by 1. And next, for the next cycle, again I have to shift and then check this bit. Now I have to check for this bit, which is unknown right now. So after shift, since the previous value of Qn is 1, it means the previous subtraction is valid. So in the next cycle, I proceed with the subtraction only, right? If the previous value of the Qn is 0, it means the result is negative. It means it should be the false subtraction. So I have to proceed by addition of divisor. Okay, but here previous value of Qn is 1, so I should proceed with the subtraction only. Okay, previous subtraction is correct. So next thing is, as usual, subtraction. 10011 is added to the partial remainder. I am getting this result. Okay, so here also, now the result, most significant bit is 0. It means the result is positive, a greater than 0. So again here, one time the divisor can go from partial remainder. Okay, so I will set now inspecting quotient bit is also 1, so that this will be 1. Now with this, 2 bits I have verified. So count have to be reduced by further 1, which is not 0. With this, 2 cycles are finished. Next cycle again, shift it left side and then perform the subtraction, because previous value of Qn is 1. So I have to proceed by subtraction. Okay. So perform the subtraction, add minus b to a, then I'll be getting this result. Again, a is 0. Most significant bit of a is 0, indicating the result is positive. So the present inspecting bit is also 1. Okay. Right. So next, reduce the counter, check with 0. It is not at 0. So again, proceed with shift and then add minus b, because the previous value of Qn is 1. So you have to add minus b, and then I'm getting this result. Okay. So here in the result, a most significant bit of a is 0. It means the result is positive. A greater than 0. It indirectly says a greater than 0. Result is positive. It is not negative. So the last inspecting bit need to be set. So I am getting Qn as 1. Now reduce the counter. It becomes 0. So the operation is finished. Okay. So this is your finally, because our quotient bit, last inspecting quotient bit is 1. So hence the remainder is in A, which is correct. You should not, or you no need to do any further modifications to get the correct remainder, because the previous quotient bit is 1 and the quotient is in this value. See, at this instant, if you receive a negative, a less than 0, the most significant bit of a is less than a is 1. It means most significant bit of a is 1. It means the result is negative. So you should not perform the subtraction to get a valid remainder. After doing this, you need to add b to this to get a valid remainder. Okay, that was the last what we call modification to be done for your remainder. After this, say as and when you reach your count 0, if you reach your count 0, if the previous value of during the subtraction, if it is less than 0, then you have to add your quotient to it to get the correct remainder. If the result is a positive, then you don't need to add anything. If the result is negative, then you have to add the reminder to get your correct reminder. Okay, this is the last step you have to be done for modifying your reminder if it is negative. So with this, we got our result as 5 and quotient as 15. Okay, right? So this is a non-restoring division. Only the thing you need to remember is suitable for 2's complement. Because of that, we got the wrong result in the last class. Okay, is it clear?
Yes, ma'am.
Okay, and next we proceed for our regular continuity, which is common bus system. We were in so common bus system. We were. So here we have talked about your CPU is having up to 8 registers and memory, out of which 6 registers and memory are connected via common bus. Okay, so any of these 6 registers and memory can places data onto the 16 bit common bus. Okay, so it can be information or data. If we talk about the registers like address register and program counter, these are of 12 bits, just 12 bits, which holds the address of your memory unit. Okay, so these are just 12 bits, and remaining registers like data registers, accumulators, instruction register and temporary registers, these are 16-bit width. Okay, out of which the registers like accumulator, data register, program counter and address registers. Okay, so these 4 registers including temporary register, these 5 registers have 3 control signals which are load, LD meant for load, INR increment, CLR meant for clear. Okay, so these 3 registers have 3 control inputs. This type of registers we usually called as binary counter. By controlling the increment input, INR input, I can increment the data available in these registers. So I can say these are binary counter with the parallel load. The 16 bits of these registers are parallelly loaded by activating the load control signal of these registers. Okay, the data from available on a 16-bit common bus, this will be loaded onto these registers at a time by activating the load control signal. And synchronous clear. Okay, so these we can clear these registers by activating the control signal called clear based on the clock input. Excuse me. So these type of registers we call them as binary counter with parallel load and synchronous clear registers, right? See, input data and output data. Input data and output data from this memory unit are connected via common bus, and which particular memory location data is to be copied onto common bus or is to be updated from the data on, from the common bus is specified by the address of that unit, which is available into the address register. Okay, so address register it helps for either reading or writing onto this memory unit. Okay, since we have only single address register which holds the data that is pointed by your memory unit. So this 12-bit address register is directly connected to the memory unit via address lines. Okay. Since we have only single address register for handling the address of the data stored in memory unit, so this 16-bit, 12-bit address lines are connected between AR and memory unit only. Okay, so in advanced processors, in the next revisions, we may have more than one register that holds the address of the memory unit. Okay, so in that case, since I have more than one register which can specify the address of the memory unit, so that many parallel lines need to be connected to the memory unit. So rather than that, there is necessity comes for introducing one more bus, which is called address bus. Okay, if more than one register is there which communicates the address information, then there need comes one more bus which is called address bus, right? So here only one register, there is no need of bus. With the simple lines I can connect. Okay, and the next register, we have this accumulator which can accept the data from 3 different ways, right? So first way is the accumulator will hold the data from adder and the logic circuit. Okay, so 16 inputs come from the outputs of accumulator, right? So outputs of accumulator, if your operation is on the register, that to accumulator, like shift accumulator, increment accumulator, or clear accumulator. Okay, then the 16 inputs coming from the accumulator are copied back to the accumulator. This is one way. And the second way, you can perform either add arithmetic and logical operation onto the accumulator from accepting the data from data register. Between data register and accumulator, the operation can be carried out and the result is transferred back to accumulator. That is the second way. And the third way, you can accept the data from input register. Okay, so this input register places data onto the accumulator. That is another way, right? See, and one more thing here, if you observe, out of these registers, 7 registers, which register data have to be placed onto the common bus is selected by the selection lines, okay, including the memory, right? So, and which register has to accept the data onto available on the common bus is selected by activating the load control signal. If it is the memory, write control signal need to be activated. Okay, so for example, if the contents of address register are placed onto the common bus, but this is having just 12 bits, but common bus facilitates 16 bits. Okay, so it means the most significant 4 bits, whichever are there onto the common bus, those are made 0. Okay, and then least significant 12 bits are updated onto the common bus. Similarly, if this address available on the common bus, if you wanted to load onto the program counter, only least significant 12 bits are taken and copied onto the PC. Most significant 4 bits will be 0. Okay, so by updating that, it will store onto the 16-bit common bus and vice versa. Okay, so this is how a common bus is available for communicating, which facilitates the data transfer between either a memory and a register or between the registers. Okay, see, this transfer is happened within a single cycle. Actually, you see, once you select the data to be loaded onto the common bus by using the selected lines, this available data is given to your ALU, arithmetic and logical circuit, right? So that data item and with the accumulator, it can perform the operation, and the result of this accumulator can be stored back to your accumulator in the at the end of the clock cycle. Okay, so this is how actual operation is carried out in the common bus. And now coming to next number of instructions. So as we already mentioned, your basic computer is having three different instruction code formats. Okay, every instruction is of 16-bit width. Out of these 16 bits, the opcode bits, whichever are there, 12, 13, 14, and 15, these bits will decide the type of instruction, whether it is memory reference or register reference or IO operation. Okay, so if the most significant 4 bits, out of which the subsequent 12, 13, 14 bits, if they are not all ones, okay, if they are not all ones, if they are having any value other than 3 ones, any value from 3 zeros to 110, okay, then that type of instruction is said to be the memory reference type. So these 12 bits, next least significant 12 bits are refer to 12-bit memory address. Okay, and I is nothing but mode control bit. This specifies the mode bit, addressing mode bit, whether it is the 12 bits are direct address or indirect address. Okay, if these opcode bits 12, 13, 14 bits, if they are both one, then the most significant bit here, if it will responsible now for distinguishing the type of the instruction between register and IO operation. If this most significant bit is 0, it is register, 1, it is IO operation. Okay, so accordingly we have 3 different instructions with which I can implement IO operations, right, or register operations or memory with memory operations. Okay, so out of the available opcode choices between 6 different choices, 3 zeros to 110, we can implement 2 operand instructions like addition, subtraction, multiplication, or logical operations like AND, OR, XOR. Okay, right? So what are the operations that we want to implement? Okay, likewise, we have 3 different instruction formats. What type of instructions I should include in my computer so that facilitates the programmer to complete his application. Okay, so as and when you have a facility, you should not include whatever you want, right? See, there should be in a proper mechanism need to be followed to implement the instruction in such a way that it is said to be a complete instruction set. Okay, there are certain rules. Such instructions you should include in your instruction set that makes the instruction set completeness. Okay, so with these 3 different formats, a basic computer can implement a maximum 25 instructions. Okay, so total 25 instructions are implemented, out of which these 7 instructions refers to memory reference, and we have 12 register reference, and then 6 IO type of instructions, all including 25 basic computer instructions. All right. See, the set of instructions that are said to be complete if the computer includes a sufficient number of instructions in each of the following categories. Only the given instruction set is said to be a completeness as and when it has some specific number of instructions in each of the following categories. Mainly, first thing is arithmetical and logical and shift operations, because ALU is the basic heart of the system which performs the operations, right? If you want to perform any arithmetic operations like addition, subtraction, multiplication, or division, which should need 2 operands, right? 2 operands you require. If one of the operand is available in the accumulator, other should come from the memory, which needs a memory reference instruction. Okay, all arithmetical and logical operations needs compulsorily memory reference instructions to implement. Okay, and then I require certain instructions for moving information to or from memory onto the processor registers. Okay, see, because your data is available in memory from which you need to read the data. So memory read instructions I should require. The read data should be loaded into a register. Okay, right? So an instruction should include a data transfer from R2 to the memory locations with respect to register. Okay, so both memory read and memory write instructions, when we talk about with respect to memory, when we talk about a register, so register should be loaded with memory data, and the register data should stored onto the memory. Such instructions you should include, because memory holds the data that has to be bring and places into your register and then perform the operation. Okay, so data register should hold contents of memory location whose address is available in AR, right? So memory contents need to be loaded into a data register. That is what called memory read operation. And the contents of the accumulator should be stored into the memory register, which we call it as a memory write operation. Okay, so you should include such instructions also. And the third type of instructions must be there are program control instructions. Okay, program transfer or control transfer instructions. Okay, sometimes you may require to repeat a set of instructions by multiple times. Whenever you want to do that, how many times you want to implement? Okay, that is indicated by certain flag bit, right? So we will usually go by a count register which is initiated by some value, and we will decrement that count register and we will check whether it reaches 0 or not. Okay, so checking the status of certain processor registers. Okay, so based on checking their status conditions, you have to proceed whether a continuous program or control transfer location. The control has to be transferred to some other locations. That can be either with respect to loops, or else sometimes we may require to call certain function which was defined in some other place. Okay, right? So in such cases, I may use a program control instructions, which are nothing but branch related operations. Okay, so that checking the some status conditions, and based on which it has to proceed with the branch. Okay, so which are conditional or unconditional branches will include in this control transfer instructions, which are must when we are implementing any program kind, right? That facilitates avoiding of repeated program writing, as we repeatedly writing the program, which wastes the size of the memory, which is one of the main important resource. So this avoids this functions or any loops will avoids the repeated writing of the same program. Okay, right? And finally, input output instructions, which should be there in any computer when we wish to read data from input device, or when we wish to indicate certain status or the output of your program onto the output devices for human interface, right? Input and output instructions are must. So if your instruction set have the sufficient number of instructions in these categories, then it is said to be instruction set completeness. Okay, so if you observe these instructions, we have certain arithmetic and logical operations like add and logical and certain memory related instructions like load and store, and certain instructions which depends on the control transfer, like branch unconditionally and branch save address. Okay, so branching this instruction, you want to change the control from one place to another, right? So whenever you want to move your control from one place to another, means you have to proceed executing from the next cycle onwards by starting from some other memory location. Okay, so some other memory location, there you have some program, from that you want to execute, right? So some other memory location, the address has to be saved in your 12 bits. So that these instructions are also comes under memory reference only, because we are referring some other memory for program. Earlier here, either load or store or logical and or arithmetic add operation. Here these are 12 bits available in the instruction, they refer data. So hence the data will be loaded into the data register and the operation is carried out. But in branching or a branching save address, the 12 bits which are available referring to the memory holds the program. Okay. So that address will be now loaded into the program counter for continuous execution in the next cycle onwards. Okay. It stores the program at that particular location, whatever the 16 bits, they are referred to the program, they are referred to the instruction code, so which is stored in instruction register, not in data register. Okay, so these two are also comes under memory reference. So since the 12 bits are now referred to memory. Okay, and next, increment and skip if 0. So this is one flag conditional status. We are incrementing certain register, and if the contents are 0, then what we are doing, we will skip and proceed for the next particular instruction. Okay, so increment and skip if 0. Okay, so here which contents we are incrementing, that will be specified in your memory location, not the register here. So the 12 bits specified in the your instruction code holds certain memory data. Those contents are incremented and they are skipped. And if the contents are 0, we are skipping. Skipping here means only the subsequent instruction will be skipped and proceed for the next instruction. Okay, so only the subsequent instruction available will be skipped. This is another memory reference type. Next, coming to the register reference, whose opcode 3 bits specifies all ones and most significant 15th bit. This is 0. Then that particular remaining 12 bits will specifies the type of register operation. Okay, so the type of operation, these 12 bits will interpret here. If the upper 4 bits are like this, which is nothing but 7, upper digit is 7, constant in case of register reference, which is 7, you can observe the same 7, and the remaining 12 bits will change its value based on which the type of operation with respect to register is varied. If it is 800, it is clear accumulator. 400, clear E bit, which is the extra bit coming out during the operation like addition. And complement accumulator and E bit, circular right, circular left, and incrementing the accumulator, and then skip the instruction if positive. Another control transfer instructions based on the conditions accumulator. Skip if negative, skip if accumulator is 0, and skip the instruction if E is 0. And finally, alt computer, which is a processor related instruction which doesn't require any of the memory address or even any of the register reference operation. It just halt the computer. It makes your computer stop, right? It won't do anything. And next instructions, input and output operations. Input, it reads the character from character and places into the accumulator. See, IO type reference instructions, most significant 3 bits, 12, 13, 14 bits are 3 as usual, even in the reference, register reference, but the most significant bit is also 1 in case of IO reference. So most significant digit is fixed to F. The most significant digit is fixed to F in all types of IO operations, and the remaining 12 bits will specify about the type of IO operation. Like read input. Input means read input, write onto output device, skip on input flag, skip on output flag, interrupt or interrupt off. These are different IO operations. So totally 25 instructions totally are used in a basic computer to specify the instructions completeness. Instruction set completeness. Okay. next timing and control. Okay, we'll see it in the next class, the timing and control, because we have an instruction available in the memory whose address is available in the PC. You need to read the instruction, which we call that as fetch operation. After that, it has to be decoded and then executed, and finally write the result onto the memory or to the accumulator. Okay, so these are the certain sequence of operations to be done, right? So with respect to some clock signal which is given the time required timing and control signals, accordingly this set of operations will be this set of micro operations will be completed at a particular time instant. Okay, see, before fetch you can't decode, before decode you can't execute. Okay, so all these three should be done in a sequential manner, right? So to do so we require a proper time control input, so which is coming from your clock signal. Okay, with respect to clock, how these operations are carried out, and you require the control signals like selection of the selected lines for a particular register, and load control signals or increment are clear, right? So these have to be generated at a particular time instances, then only the operation is a valid and it is in sequence manner. Okay, so that timing and control, how it is happening in a basic computer, we will see it in the next class. So that's all for today. So if you have any doubts, you can ask me. Meanwhile, I will take the attendance. Who is 33? Mutyam, 33.
Yes, ma'am.
You are from E1, right?
Yes, ma'am.
Why you joined here?
Ma'am, this is DSP class, right?
No.
Okay.
Till now you don't know what class you are listening.
Yes, ma'am. It's looking like computer organization related.
Yes.
We're telling you.
Amma,
So
you have
really
a DSP class. You are final year?
Yes, ma'am.
Final year E1, you have DSP class afternoon, right? Check the timetable.
It is showing entrepreneurship class, ma'am, but there is no link provided. Sorry, ma'am. Just sorry.
You just leave. Yes, let me collect the attendance. You have any doubts, you can ask. 67. $69. $86. 92. 100. 110. 112, 113, 116, 120. 100, 112. ఇప్పుడు జాయిన్ అయ్యారమ్మా. Next time after 10 minutes, I will log the meeting and you are not supposed to allow to join, okay? After 10 minutes of the class begins, I will log the meeting. Okay, thank you, Amma. Bye for today. You please practice non-restoring division algorithm also, okay? You practice for 2 to 3 examples. If you have any doubts, you can ask me in the next classes. Thank you. Bye for today.